In this video, I'm going to be evading an anti-satellite missile with my space station that's filled with $1 million.
Welcome to Basic Orbital Mechanics, where all your dreams come true and that D in your high school math class serves you well. Maybe not. Anyway, let's get started. Okay, step 1. Imagine you have yourself a planet, and you're orbiting that planet. In this diagram, you don't have a perfectly circular orbit. This is called an elliptical orbit. This is very useful for describing this first step. So that planet has a center. For this elliptical orbit, you have your closest point to the planet and your farthest point from the planet. And so we'll label those R sub 1 and R sub 2. R sub 1 is your periapsis, and R sub 2 right here is your apoapsis. So what we're going to do with this, we're going to find the semi-major axis. So what that is, it's defined by the variable A. A is equal to R1 plus R2 divided by 2. So the semi-major axis, this right here, semi-major axis, is very important because we're going to be using that later in our equations. So the semi-major axis is equal to the distance of our periapsis plus the distance of our apoapsis divided by 2. And so it is the value of this whole distance here cut in half. All right, step 2. The constant G is the universal gravitational constant, which is equal to 6.6743 times 10 to the negative 11. It's the force of gravity through the entire universe, essentially. You can see with that negative 11 there, that makes this a very, very small number. It is, in fact, the weakest force in the entire universe, which is very counterintuitive, I know, because you see it everywhere. But it is the weakest force in the universe. All right. Step 3. So we have our planet, and we have the center of the planet. What we want to do is determine our velocity at any point around our elliptical orbit here. So again, we have R sub 2 and R sub 1. Now, to find the velocity, let's just make a little radius here. And we'll have a little rocket. Let's make our rocket a little circle. And so this rocket is going around the planet at a certain velocity. And so this radius here is going to be defined as R. Now, to find our velocity, that equation is defined by v squared equals gm times 2 over r minus 1 over a. And so this here is our velocity. That right there is the gravitational constant. That's that value right there. M is the mass of our planet. So M is the mass of whatever object we're orbiting. And so we're multiplying that by 2 divided by the radius that our object is traveling minus 1 over a. And so a is that semi-major axis. Be sure to pay attention to that semi-major axis for your situation. It will be very embarrassing when you choose the wrong semi-major axis and your calculator spits out 0. So this equation can be rewritten as v equals the square root of gm 2 over r minus 1a. So if we want to find the velocity for our elliptical orbit, v sub ELL sub ellipse equals v equals 2gm over r minus gm over a. And so the a again is that sum of the two radii divided by 2. To find the velocity of a circular orbit, a perfectly circular orbit, it's a little simpler. So v sub CIR equals the square root of gm over r. Much simpler than the last one. All right, whatever step we're on, 4. So this is just some more information. The mass of the Earth, that would be this value right here, m sub Earth, is equal to 5.972 times 10 to the 24 kilograms. And the radius of the Earth is equal to 6,371 kilometers. Now, we're using the SI units here just because they're easier to work with. I want to put some attention to that. We will not be using kilometers. Instead, we're going to be using meters. Not that we're going to use the radius of the Earth here. We'll be using like radius of our object from the center of the Earth. But we want to be using meters because we're going to be working in meters per second and not kilometers per second. And so we want to keep our units consistent right here. Step 5. My space station is in orbit around the Earth at a certain radius. And to evade this missile, I need to move it to a higher orbit. And so I have my Earth right here, center of the Earth. This orbit right here is the orbit of my space station as it is right now. And I want to move it to a higher orbit. How do we do that? Well, you could say, burn the engine. Well, you'd be precisely correct. So we're going to have, this is our point A right here. Our space station is orbiting the Earth counterclockwise. And so to cause the orbit to reach a higher orbit, what we want to do is point in a prograde direction. And so since our spacecraft is orbiting counterclockwise, we're going to be pointing the rocket in a prograde direction, which means forward, retrograde means backward, prograde direction, and burn the engine. And so what that's going to do is that's going to extend the other side of our orbit to where we want it to be. And so this would be point B. So that's going to cause our orbit to be an elliptical orbit. So once we reach point B, we're not done. We have to burn another prograde burn in order to cause our orbit to be perfectly circular again, just at a higher radius from the center of our planet. So that's going to take a certain amount of fuel. In other words, it's going to take a change in velocity. We want to find the change in velocity first for A and second for B. So delta VA equals V for the ellipse minus the V for the circular orbit. That triangle there is delta, which means change in. So change in velocity for A equals the velocity of where we would be for the ellipse minus the V for our original circular. To find the delta V for our orbit starting at point B, it's going to be delta VB equals, and then it's just the other way around, V circular minus V ellipse. And so what we're going to be doing is we're going to be putting these equations into that. So delta VA equals 2gm over r minus gm over a minus gm over r. And so what this is it's multiplying 2 times the gravitational constant times the mass of our planet divided by the radius that we are from the center of that planet minus gm over a. And so since this part is the equation for the velocity at the ellipse, we're going to be using the a for this distance right here, not the a for the original circular orbit. It is going to be the a for the distance of the periapsis and apoapsis of the ellipse. And so then we're subtracting it by the velocity for the circular orbit. And so remember, that's these two equations up here. And so it's the velocity for the ellipse minus the velocity for the circular. The velocities I'm talking about are what the velocities at point A would be for each type of orbit. Now I'm just going to go ahead and write down the velocity for orbit B. The change in velocity needed at point B in order to change it from an elliptical orbit to a bigger circular orbit is just the exact same thing. It's the velocity at the circular orbit minus the velocity for the elliptical orbit, and that's all for the instance at point B. Now what we're going to be doing is plugging in some numbers. So we have our Earth right here. We have the center of the Earth. Let's label this Earth. And we have our orbit. This is the orbit of my space station right now. And so the radius from the center of the Earth of my space station is 500,000 meters, aka 500 kilometers. And the orbit I want to reach is at a height above the center of the Earth of 2 million meters, aka 2,000 kilometers. So what we want to do is change this orbit. So this is my point A, this is my point B. I'm going to change my original circular orbit to an elliptical orbit to reach point B, and then from that elliptical orbit to a circular orbit again, a larger circular orbit. So I'm going to start plugging stuff into the equation. Let's keep in mind the A's for each value though. So I'm going to outline the elliptical orbit right here. The A, the semi-major axis for our original orbit, is 500,000 meters. Right there. My A for the elliptical orbit is going to be the distance from A to B divided by 2. And so A equals 1,250,000 meters. And so this A is for the value of that distance right there. The A for my final circular orbit is 2 million meters. Now what we're going to do is we're going to find the change in velocity needed to make our space station go from point A to make the orbit an elliptical orbit that reaches point B. So using our equations, that will be delta VA equals the square root of 2gm over r minus gm over a minus the square root of gm over r. Now keep in mind, this a is the a for the distance from A to B, 1,250,000 meters. It is that a right there. And so now I ran this through. You can probably do it on your own if you want, but that's a lot of numbers. I already ran it through all the numbers. Delta VA equals 79.34 meters per second. You can box that. That is the required amount of change in velocity you would need at point A to move it from that circular orbit to the elliptical orbit. Now, delta VB would be to change from the elliptical orbit to the larger circular orbit, my goal height around the Earth. So that equals the square root of gm over r minus 2gm over r minus gm over a. So for delta VB, that is going to be the other way around again, as I said. It's the velocity at point B for the new circular orbit minus the velocity at point B for the elliptical orbit. And so this A value, again, is the A value for the elliptical orbit, 1,250,000 meters. Running through the equation, delta VB equals 5,188.51 meters per second. Box it, you done. So this is the value of the change in velocity we need to ignite the engines in order to make this original circular orbit go to the elliptical orbit, and then delta VB is the change from the elliptical orbit to the larger circular orbit. So now I know how much I need to burn the engines in order to change my velocity to reach these new orbits.
Absolutely.